Hello again, it's John McGready with the fifth installment in the Interview with a Famous Statistician series. And today it's an honor and a pleasure to have Dr. Roger Peng, who's on the faculty of Biostatistics here at the Johns Hopkins Bloomberg School. Roger actually does a lot of work at the interface of statistics and environmental health, and he got his degree in statistics at the University of California at Los Angeles. He came here to Baltimore to be a postdoc in the department, and we luckily were able to retain him as faculty, and he's now an associate professor in the department. So Roger, let me welcome you to the interview series.
Well, thanks for having me on, John.
I'm thrilled to have you here. So Roger, you've been active at the interface, as I said before, of statistics and environmental health, among other things. Can you comment maybe on one or two major contributions to environmental health vis-a-vis statistics in the past decade or so?
Sure, yeah. So statisticians have made an enormous contribution to the area of environmental health, in particular my area, which is air pollution epidemiology. In part because of the excellent group of statisticians that we have here in the biostat department at Johns Hopkins. One of the important areas where statisticians have made a contribution in air pollution epidemiology is in the issue of model selection. So the idea that, that we run a lot of these regression models to estimate health effects of ambient air pollution, and of course the models are fairly complicated, and there's no way to know exactly what's the correct model or what's the best model. And so we have to be able, so our uncertainty about that model needs to be factored into the analysis. So understanding how that uncertainty is played out in terms of the estimation of the health effect is one of the areas where we've developed a lot of statistical methods to both account for that uncertainty in the estimation of the health effects and to kind of explore it through things like sensitivity analysis.
Excellent. So you add in, on top of the sampling variability, you add in uncertainty about the selection of the model and how you proceed to analyze the data.
Exactly right. So we have the usual kind of uncertainty just from having finite samples of data that we account for in things like standard errors. But there's also another level of uncertainty that in the past people had generally ignored, and where we've kind of developed methods to kind of explore what is the effect of not knowing what the right model is, and how does that affect our inference about what the health effects are.
Excellent. So what kind of generally have you found, and how does it sort of relate to the science of public health in general?
So one thing that we found, so I work mostly in an area that's called looking at acute effects or short-term effects of air pollution on population health. And one thing one of the big issues with the modeling in this area is that there are lots of factors that we don't directly measure. And so these unmeasured confounders are difficult to control for because they're unmeasured. And
right.
So you have to think of ways to try to capture the variability that's attributable to those confounders without actually having direct measures on them. And so we've developed a lot of kind of models using things like splines and smoothers to account for that unmeasured variability. And in some cases we found that in some of our national studies, we found that the effect of these unmeasured confounders can be big for some outcomes and some pollutants, or it can be very small. It kind of depends on what you're looking at.
Excellent.
Yeah.
Okay. Well, one thing I wanted to mention as well, we've met Jeff Leake before, and Roger's another co-editor of the Simply Statistics blog. So he's got his finger on the pulse of statistics and biostatistics, both because he's an excellent statistician, but of course because he's doing the blog as well. And so I wanted to ask you, Roger, what do you see as some of the notable opportunities for statistics and biostatistics in the next few years?
Well, I think now is just one of the most exciting times to be a statistician, to be involved with data, and to be able to analyze the data. I mean, there's so much data being produced and stored everywhere, coming out of every industry, every business, every technology. And I think the demand for statisticians is just going to increase, in the near future exponentially. And so I think there's a lot of areas in terms of kind of merging different types of data together to kind of create new value. I mean, so that's related to essentially a lot of what I've done. We've taken large national databases of health data, environmental data like air pollutants, weather data, and brought them together to do kind of large national studies.
And that's no easy task, getting these systems to talk to each other, linking them up, et cetera, right?
Right. So there are some of the more kind of technical issues of kind of how do you get these databases to link together. But then once you've got them all linked together, how do you develop the models to kind of look at associations between data in one database and data in another database that were never really meant to be linked together in the first place.
And they're measured at different levels of observation, right?
Right. Some are measured every day, some are measured on a month, some are measured at a zip code, some are measured at a county level. So there's all kinds of aggregation types of problems. And I think having the skills, this is just one small area where I think having the skills to deal with very heterogeneous data like this, not just in air pollution epidemiology, but in other kinds of areas, is extremely valuable because I think the ability to kind of bring different types of data together will kind of allow people to kind of create new products and create new insights into answering important questions.
Excellent. Yeah, no, it is a very exciting time to be a statistician.
Yeah.
So, I'm doing these interviews in the context of the statistical reasoning series, which is sort of an entry-level course into the realm of biostatistics. And we pack a lot in 2 quarters.
Yeah.
We go everywhere from exploratory data analysis up through and including multivariable regression
Sure.
for continuous, binary, and time-to-event outcomes. And of course, we cast that into context of the multiplicity of predictors and also confounding and effect modification.
Mm-hmm.
You do some very sophisticated, mathematically intriguing work on models, model selection and stuff. How does that build, and how is it informed by sort of these ground or first principles of biostatistics?
Yeah, sure. So I think one of the things, it's funny, I sometimes lose sight of this a little bit because I've been working in this area for almost 10 years now, and a lot of the techniques that we've developed are, we've kind of refined them and honed them, and we understand them quite well. And so when we apply them, it just seems like second nature. But you forget that, back when we were first starting out, we didn't have all the ideas in place. So a lot of what we did is just very basic exploratory analysis, pairwise plots, looking at correlations, understanding, so that help us kind of build the models that we use routinely today. And so things like exploratory data analysis are extremely valuable in terms of just plotting the data and looking at kind of bivariate relationships. Of course,
it's good to hear this from multiple people, because I sometimes think that gets swept under the rug.
Yeah.
Like it doesn't immediately seem sexy or gratifying, like fitting a model, but it's an incredibly important part of any data analysis.
Yeah, and it's easy to forget because oftentimes you'll kind of do the exploratory data analysis and then figure out, okay, I think this model looks appropriate, and then you'll kind of apply that model many different times to different kind of similar problems. And then you think, oh, well, we've always had this model.
Right, exactly.
And you forget about all the work that went into to kind of figure out what the right form is or what the appropriate kind of variables to include, things like that. So that, I think, was a key part of what we did many years ago. And of course, the fundamental thing that we use is regression, right? And we use generalized linear models, so we use Poisson regression, but really we just use regression modeling. A lot of the techniques in terms of looking at so we have a lot of nonlinear relationships. We use things like splines to adjust for, and so discovering those kinds of nonlinear relationships, with added variable plots and whatnot. So we use, those techniques are really just fundamental techniques, I think, that we've applied throughout to help us kind of build up into something more complex.
Excellent. So as we conclude, not really concluding, but the last thing I want to talk to you about is, where do you see your research going in terms of air pollution effects, et cetera? Because this is a really exciting area. It's very important in terms of setting regulatory policies in the United States and internationally, and there's a lot of interest in this. And as you noted before, the ability to collect more and more data is growing in leaps and bounds. So where do you see yourself taking this research, or where do you see it going in the next few years?
Well, okay, so where it's going and where I'm going are two different things, obviously, because the field's very big and there's lots of interesting questions to ask. For me in particular, just for a little bit of background, the way that the U.S. regulates pollution is the EPA has a national standard, and then they set the level at which pollution can't exceed, and then everyone kind of has to figure out how we're going to meet that level. So one of the ways that they regulate, for example, particles, they just say that the level of particles can't be above a certain level. But particles come from all kinds of different sources. They come from cars, they come from coal-burning power plants, they come from diesel trucks, they come from the desert, they come from all over. And what's not as well understood is whether the particles that come from one source are equally harmful as particles that come from another source. So if the particles coming out of the exhaust pipe of a car, is that the same as the dust that comes off a farm in the southeastern United States, for example? And so understanding kind of what are the differing health effects between different sources of pollution is one area of intense interest for me, in developing statistical models to kind of look at this on a national scale is something that I'm very interested in. And the long-term goal, and this is not going to happen because this will require kind of a lot of changes in regulation, but the long-term goal is to try to to develop the scientific basis to regulate pollution in a much more efficient and kind of targeted manner. Because right now, if you want to say lower air particulate matter, you just have to kind of go to every source and say produce less.
Right, right.
And so, but if you could figure out, okay, well, these particles are really the harmful ones, then you could target specific sources and have a much more efficient type of policy.
Very interesting. Yeah. Excellent. Well, Roger, I want to thank you so much for coming out today. I appreciate it. I'm sure the viewers do. And until next time, I'm John McGready, closing out with Roger Peng. Thank you very much.